As an example of circular motion problems, I'm going to first solve this problem. So in that case, we have two masses in here which are connected to a string, and they are basically rotated around this point in here. And the lengths of these two portions of the string are the same. And we would like to find the ratio between the tensions in these two strings. They are also rotated on a horizontal plane, meaning that, well, there is no gravity in here. So you can think of it as some kind of a system which is rotated on top of a table, but the table is a little bit wider than this, all right? Just keep this in mind. So to be able, since they are asking for the ratio of the tensions, probably we need the ratio of these accelerations in here, and probably the ratio of the velocities as well. So at some point we would like to also find these ratios, but first let us see why we would need this ratio in here. For this, I need to draw the free body diagram. So let's do it like that. So this is not a constant acceleration motion. So as a result, the acceleration is different at different times. So in that case, of course, we have to look at the motion at a single given moment, like this one in here. So I'm going to draw the free body diagram at that moment. So let's say that at that moment, this has an acceleration a1, and this has an acceleration a2. We know that these are towards the center of the motion. So I only need the accelerations in here, and then I draw the free body diagram. So for the first one, I have a force which pulls this thing in the leftward direction, applied by this string, and this string pulls it to in the outward direction. So that's T2. On the second object, we have this string which is pulling it in the leftward direction, so therefore this is tension T2, and there are no other things. So basically these masses, these objects are interacting in physical interaction with the strings, and so therefore the strings are the ones that apply a force on these. So no gravity in here again, so we don't have any gravitational force. And so therefore there cannot be any other force. And then let me also show as an extra in here the directions in here, A1 and A2. Okay, just as in the previous cases, I'm going to choose an axis. So I'm going to choose the positive x-axis in the leftward direction, and then write down the net force is equal to mass times the acceleration equation. So on the first one, on the first object and on the second object, and obviously the net force on the second object is equal to mass times its acceleration. So what we do, again, we just write down the x components. So T1 has an x component which is plus T1, and T2 has an x component which is minus T2. The acceleration A1 has an x component which is given by this component in here, so that's plus A1. Right, let me do the same thing for this thing in here. So in that case, for the second mass, the tension is T2 and the acceleration is A2. Okay, so in short, we have T1 minus T2 is equal to MA1, T2 is equal to MA2. So therefore, from here, we just deduce that T1 is equal to M times A1 plus A2. Let me go to that side, therefore. So in that case, if I write T1 divided by T2, the masses cancel, and as a result, I'm going to get A1 divided by A2 plus 1. So as a result, I need to find the ratio of the accelerations. Let me go back. How do we find the ratio of the accelerations? Or let me open a new page in here. So in that case, we would like to think of the motion like this. Both of these are circular motions, so let me just draw these yellow circles. Yeah, well, these are not perfect shapes, but the idea is that, of course, you should be able to understand what we are drawing in here. So since the first circle has a radius r, it has circumference 2 pi r. And this one has a radius 2r, so therefore it has a circumference of 4 pi r. So we know that they have the same period, right? Same period. Let me call this as the capital T. So therefore, I can express the speed v1 as the distance traveled divided by the period. And speed v2 is distance traveled divided by the period. And the periods are the same. So from here, we can then find the ratio of the speeds. So that's going to be equal to 2. So it turns out that on a circular motion around the same axis with the same period, the ratio of the speeds is the same as the ratio of the radii. So we are going to see that this thing is a general rule later, but right now let's just try these. And in that case, if I express the acceleration, a1 would be v1 squared divided by r, and a2 would be v2 squared divided by 2r. So therefore, a2 divided by a1, let's say it like this. This is v2 divided by v1 squared, and then 2r in here. Let me express it like this. So in that case, this is 2 squared divided by 2, so that's again equal to 2. So the ratio of the accelerations, or the ratio of the velocities, or the ratio of the distances to the center, they are all same. That's basically the conclusion in here. As I said, I'm going to talk about this later. When we see the rotational motion, we are going to see this systematically. So in that case, this is 1/2. So therefore, the ratio of the tensions is equal to 3/2. All right, that's basically the end of the question. However, let's also talk about the wrong ways of solving this problem. Let's say it like this. Some people solve it like that. They actually add, on the free body diagram, they add something like that, mv1 squared over r in here. And on this one, is mass times v2 squared divided by 2r. Okay, so let me just say this. I mean, if you're basically thinking about solving this problem by using this kind of a method, so there are actually a few things wrong in here. So in this approach, probably you're taking the accelerations to be equal to 0. So you're basically assuming that they don't accelerate. But we know that, I mean, we're basically solving these problems to be able to understand the concepts correctly. And so as a result, if you actually contradict with the basic concepts that we have learned about the kinematics, for example, then this is actually, the method that you're applying is not useful. So we know that in circular motion, there's an acceleration. So that's one of the first things. So if this mass in here is doing this motion in here, and if the velocity changes its direction, so we have said that the acceleration is due to the change in the velocity, and velocity is the vector. If the velocity changes direction, then it is changing, so therefore there is an acceleration in here. So there is no way that you cannot have an acceleration in here. So that's the first thing wrong. The second one wrong is that, well, it's about the force concept. About this force in here, as supposed force, we have said that the force is due to an interaction between two physical objects. However, for that force, we don't have an object that applies this force. So what is it applying? I mean, is there a third object in here that applies this force? And this one too. So we cannot answer that question. So if there is no physical interaction, then there should be no physical force. So just remember this. There are 4 known forces in nature. So these are basically 4 mechanisms for different objects, different particles to interact with each other. One is the gravitational force, gravitational interaction. So the weight force is the corresponding force. The second one is the electromagnetic. Most of the time, this is the Coulomb force. It's the force between the electric charges. So therefore, it's an electric force. And then there is this weak and the strong force, which we never observe. So this thing in here is none of these. It's not a fifth kind of force that an object, it's applied on an object with the absence of a second object. No, that's actually, conceptually this is wrong, right? So as a result, if you are thinking about solving these kind of problems like that, just forget about this. There's actually some kind of a method that looks similar to that. It's basically a method of accelerated reference frames, but we are going to come back to this. As a result, if you want to learn something about this, then please wait until we talk about what happens in the accelerated reference frames. Okay, so as a result, do not apply this. Just use the basic concepts in here because you have to know the correct way of solving this problem. Basically, list all the forces. List all the forces that are all the physical forces that act on the objects. Find acceleration, and then just write the Newton's second law. Just equate the sum of all the net forces, all the physical forces, to mass times acceleration. All right. So without learning how to use this thing, we shouldn't actually try any new ingenious methods. Okay. Let me stop in here.